Okay guys, in this video we're going to do a couple of physics problems. Um, there's a whole longer story than the little story I'm going to tell you right now, but basically the idea is Newton's first law has two parts. The part that I want to talk about is if an object has a bunch of forces acting on it, but the object isn't moving and it just never moves, then the total of the forces has to be zero. Think about, for example, if you have like a book resting on a table. Okay, so let's pretend that's a table there. Okay, here's some legs. And you have this book resting on the table here. Well, there's a couple of different forces on the book. There's its weight. Weight force, by the way, is always downward. Usually when I write down forces, I'll write them, they're vectors. Forces are vectors, but I'm going to put the tail of the vector on the object. But why doesn't it go down? Because there's another force pushing upward. The table is pushing it upward, not letting it fall down. So we have the second force. So the blue force is the weight force. Weight forces always point downward. Actually, downward is not the correct way to say it. Weight forces always point towards the center of the Earth. But yeah, when we're, weight forces look like they're downward. If we were doing some kind of problem where we're really far away from the Earth, then you might have to point it in weird directions, but make sure it's pointing towards the center of the Earth. But if you're just on the surface, standing on the surface of the Earth, weight force points downward. The other one that's pointing upward, incidentally, has a name. It's called the normal force. I'm just going to put a little n. Anytime an object is touching a surface, the surface pushes on that object, and it's always perpendicular to the surface. So since the surface is this way, the normal force is this way. The book does not move. What that means is even there are forces on it. There's two forces. There's this one and this one. The total of the forces has to be zero if an object is not moving. Again, that's not all of Newton's first law, but that's like the first half of it. You've probably heard of it as if the total force on an object is zero, then if it's at rest, it remains at rest. So in other words, if you have an object that's at rest the whole time, then the total of the forces is zero. Okay, so we're going to do a couple of problems where an object is at rest and has a bunch of forces on it. And then in order to answer the question, we just have to realize the total of the forces is zero, and then we can go ahead and answer the question. So let's go ahead and take a look at this first problem here. A block and tackle pulley hoist is suspended in a warehouse by ropes of lengths 2 meters and 3 meters. The hoist weighs 350 newtons. 350 newtons is a weight. By the way, don't forget that a weight is a force and always points downward towards the center of the Earth. The ropes fastened at different heights make angles of 50 degrees and 38 degrees with the horizontal. Find the tension in each rope and the magnitude of each tension. Okay, I guess we didn't talk about tension yet, but basically the idea is, again, I'm not going to say a whole story. Let me just say this much. If you have a string, a rope, that kind of thing, pulling on something, the force due to the string is called a tension. And tension is always along, if you're trying to figure out what the direction of the tension force is, it's always along the direction of the string. So this says find the tension in each rope and the magnitude of each tension. So magnitude, we know what that means, but then it says find the tension. Tension is a force, so they want us to write it as a vector as well. So they're asking us for two forces, two tensions, because there's two ropes, and then find the magnitude of each one. Okay, so let me go ahead and look at a smaller picture here. Okay, so this problem is slightly tricky, but I'm going to make it real easy in a second. Because there's really so many forces going on. When you're doing a physics problem, you usually want to think of the object as just a dot. You see we have this big object over here, but I kind of really want to just think of a dot. I'll make it kind of big here. And I want to see all the different forces on it. Well, you might say, well, if this is the object, then it's being pulled upward by this contraption here. But then, okay, this, we have these different forces over here. Which one's acting on which one? So here's the trick that I'm going to give you for this problem. The object I want you to focus on is this point right here. This point right here. Or if you want, you could think of that little circular thing there. That could be your object. And you could see that that object is not moving. and it's got 3 forces on it. So if I zoom in on that little ring, let's go ahead and just think of the ring. So if the ring is the object, well, what do we have? We have a tension force. Remember, tension force is along the direction of the string. So we have a tension force that way. We have another tension force this way. I don't know how long those vectors are. And then we have a weight force because something is hanging on and pulling it down. So we actually have 3 forces on that thing. So the idea is we're going to have to write down what those 3 forces are, and then say, okay, the sum of those forces has to be 0, and then see what we get from there. So, okay. Here's our object. In the physics class, they'd call this a force diagram. So we have a force downward due to the weight of the pulley. I'll just go ahead and call that a weight force. Then we have a tension force this way along the direction of the string that's holding it that way. Let me call that force tension 1. And then we have another tension force along the direction of the other string. I don't know how long that one is. Let's call that tension 2. Okay, so we're going to write those forces down as vectors. Whenever you want to write a force as a vector in component form, you want to put an x and y axis down. So I'm going to go ahead and draw an x and y axis here. And it's easiest to do it in such a way that the object is at the origin. So we'll draw an x-axis like this, and a y-axis like this. Okay, so I want to write down what each of these forces are in component form. The weight one is the easiest one, so let's start with that one. This is a 2-dimensional problem. You can see the weight force only points in the y direction. That means there's a 0 for the x component of the weight force. The y component of the weight force, well, it's just however long this vector is. Can you see that it's negative because it's pointing downward, but the y-axis points upward? So the y component is negative. Negative what? Whatever the weight was. Now back in the problem, I'm looking back at the problem in the book right now, and it says the hoist weighs 350 newtons. 350 newtons. If you haven't heard of newtons, it's the SI unit for weight force. So basically the length of this arrow is 350 newtons. So that is the weight force right there. I'm not going to put any units in there. Okay, so that's the weight force. No x component because it only points in the y direction. Y component is negative 350. Okay, now let's go ahead and try to find these 2 tension forces. Okay, so let's work on T1. So what I'm going to do just to make T1 easier is I'm going to draw another picture. So I'm going to draw a blown up picture here of just T1. So that's the T1 vector. I'm going to label the length of it T1. I mentioned this before in class, that if you put an arrow on top, you're talking about the vector T1, but if you don't put the arrow on top, or if you don't put it in bold, that's going to be the length of the vector. So T1, that's the length of it. If that bothers you, you can put an absolute value. Actually, why don't we go ahead and do that? Maybe that'll make it easier. So the length of the vector is absolute value of T1. Now what I want to do is I want to find the x and y components of it. The way you find the x and y component of a vector, well, if it's drawn with the tail at the origin, then it's pretty easy. What you do is you go from the head or the arrow, and you go until you get to one of the axes. Let's just go ahead and go from this tip. So we'll go from the tip of the arrow down to the x-axis here. Okay, and the length of this is the x component. Well, let me call the length of that triangle x, the length of that y. So you go from the tip of the arrow down to the x-axis or down to the y-axis, and then the vector that goes from the origin to this point here is one of the components. And then from this point up to the arrow of the original vector, that's another component. Since this one like this is in the x direction, that's the x component. Since this one here is in the y direction, that's the y component. Also notice they're both going to be positive because the x component is pointing in the direction of the x-axis and the y component is pointing in the direction of the y-axis. Okay, so now what we're going to do is we're going to use some trig, but I need an angle first. Now, if you looked back at the picture, the problem said that this rope made an angle of 30 degrees with the horizontal. I guess the easiest way to show that here is to put this, they had some kind of angle right here. If you think of this, the dot is like the ceiling or whatever, this dotted line here, then it made that angle of 38 degrees. Well, I don't want that angle, I need an angle in my triangle. Well, if this is 38 degrees, then you could figure out this angle because the total of these has to be 90. So that would mean this is 58. Or you could figure out this angle a couple of ways. If you figured out this is 58, you could do 90 minus that to get this, because remember they have to add to 180. You know, this is a 90-degree angle. So 90, 58, and 52, and whatever this is has to be 180. Or there's a result from geometry that said if you have parallel lines, then alternate interior angles are equal. So anyway, this angle here is 38. Okay, so this is the 38 they gave in the problem, but I need this one because it's in my triangle. So again, you can use the 38 like I'm going to do here. I'm going to put this as 38. Or you could use this angle here if you want. It doesn't matter. Point is, get an angle in your triangle. And then we'll use SOHCAHTOA to figure out what x and y are. So, sine of 38 degrees that's going to be opposite over hypotenuse. It's going to be y over absolute value of t1. I guess if I put absolute value of t1, I'm supposed to set arrow there. So this tells me that y is the absolute value of t1 sine 38 degrees. If you multiply both sides by absolute value of t1. Same thing if you do cosine of 38 degrees is going to be adjacent over hypotenuse x over absolute value of t1. So that means that x is absolute value of t1 cosine 38 degrees. And then now we're going to go write down t1 in component form. And when I do that, you have to remember this sine, cosine business using SOHCAHTOA, everything is positive when you do that. But now you got to go and check and see if any of the components are negative. But as I said, the x and y components are both negative. Both positive. If they were negative, you'd have to stick in the negatives yourself right here. But they're not, so we can just go ahead and put them in. So the x component is the one with the cosine in it. So we have t1 cosine 38 degrees. And the other one is absolute of t1 sine 38 degrees. Don't put any negatives in there. Okay, there's the t1 vector in component form. Okay, now let's go ahead and work on the t2 vector in component form. So I'm going to erase this part. We're going to do the same thing again. We'll draw the vector, we'll draw the components, we'll make a triangle, get an angle in there, and use SOHCAHTOA to figure out what the components are. I think this time at least one of the components is going to be negative, so you do have to watch out for that. But once again, when you do SOHCAHTOA, everything is going to be positive. Okay, so I'm going to draw the t2 vector this time. So here's the x-axis, here's the y-axis, and the t2 vector points like this. I'm going to put absolute value of t2 for standing for the length of the t2 vector. And again, I need to find the component. So you can go, like I said, from the tip of the arrow, the tip of the vector, to either the y or x-axis. I don't care, just get a triangle. I like to go to the x-axis, so we'll just go down here. But it doesn't really matter. And then to get the two components, well, one of them is what you get when you go from the origin to that point you just got to. That's one of the components. You know that's going to be the x component because it's in the x direction. And then if you go from there up to the original arrow of the original vector, that's going to be the other component. That's the y component. I'm going to call the length of this x, the length of this y. Okay, and then we'll figure them out, but we need an angle. And then, like I said, once we find them, when we write the vector down, we might have to have a negative in there somewhere. Okay, so the problem said, we'll go back to the book. I know you can't see this now, but if you go back to the book, it said that this rope makes an angle of 50 degrees with the horizontal. So if I draw like this is the roof or something, then they gave you 50-degree angle right here. And so that means this angle here is going to be 50. Okay, you can do it by saying, hey, that's got to be 40, and oh, therefore that's got to be 50, or just realize we have parallel lines here, so those have to be both be 50. Again, you can use the 40 instead if you want, but I like to use the one that's in the problem, so let's use the 50. So now we're focusing on this triangle. We're going to use SOHCAHTOA. So sine of 50 degrees. Don't memorize it. Look at the triangle. Sine is opposite of hypotenuse. It's going to be y over absolute value of t2. That means y is absolute value of t2 sine 50 degrees. And then cosine 50 degrees is going to be x over absolute value of t2, which means x is absolute value of t2 cosine 50 degrees. Okay, and now I'm going to go ahead and write the vector in component form. Up here, t2. And when you write it in component form, just remember if you need to put a minus sign or not. The y component is pointing in the same direction as the y-axis, so it's going to be positive. But the x component is pointing in the opposite direction as the x-axis. X component is going to be negative. So when you go to write the x component, you're going to write this, but you're also going to put in a minus sign yourself. So that's going to be negative absolute value of t2 cosine 50 degrees. And then the y component is going to be positive, so just absolute value of t2 sine 50 degrees. All right, now let me erase all this stuff. So when vectors are not pointing in the x or y direction, you have to break it up into its components so you can work with them, because we know how to add and subtract vectors and do other things with vectors easily if we know it in component form. That's why the weight one was so much better. It was just in the y. But since the two tension forces are slanted, you had to find the x and y components of each. So it took all that work to find that. But now you need to remember that the sum of the forces is 0 because the object's not moving. So in physics, you write something like sum. This stands for sum. Sum of the forces on the object is equal to the 0 vector. Remember, when you add a bunch of forces, you're adding a bunch of vectors. When you get 0, what do you mean you get 0? I mean you get the 0 vector. That means if you add w and the vector t1 and the vector t2 together, you get the 0 vector. If you add those vectors real quick and we just write it in component form, here's what you get. So I'm trying to add all three. Remember how you add them? You add the x components together. So you add this and this and this. When you're done, you get absolute value of t1. Well, you get 0, but I'm not going to write the 0 down. Plus absolute value of t1 cosine 38. Minus, sorry, it's minus. Well, it's plus and negative, so just minus absolute value of t2 cosine 50 degrees. And then when you add the y components, you're going to get negative 350 plus that. So negative 350 plus absolute value of t1 sine 38. Ran out of room here. Plus absolute value of t2 sine 50 degrees. And then that all has to equal the 0 vector. Wow, that got pretty sloppy. All right, so, and, oh, sorry, this is two-dimensional stuff, so the 0 vector should only have two components. Okay, now the next thing we're going to do is whenever you have two vectors equal, we have this nasty long-looking vector equals this vector. Whenever two vectors are equal and you have them in component form, then the components, corresponding components have to be equal. In other words, whatever's written before the comma, the x component, has to equal whatever's written before the comma here, the x component. Those two things have to be equal, and then the y components separately have to be equal. And so that's going to give us two equations. So I need some room here, so let's get rid of this. Okay, so we end up getting absolute value of t1 cosine 38 degrees minus absolute value of t2 cosine 50 degrees equals 0. This is just a regular equation now. And then the other one is negative 350 plus absolute value of t1 sine 38 degrees plus absolute value of t2 sine 50 degrees equals 0. Okay, I guess I can erase this now. And what you end up getting is a system of equations that you need to solve. System of equations from back in Math 50 or whatever. What are we trying to solve for? We're trying to solve for absolute value of t1 and absolute value of t2. Notice both equations have absolute value of t1 in it, and both equations have absolute value of t2 in it. Okay, so I'm going to need to erase this picture because I just need a lot of room here. I'm going to call this equation 1. I'm going to call this equation 2. So if you take equation 1 and you move this term to the other side, if you add absolute value of t2 cosine 50, and then you divide by cosine 38, so you can get absolute value of t1 by itself, you get absolute value of t1 equals absolute value of t2 times cosine 50 degrees over cosine 38 degrees. Okay, and now what I'm going to do is I'm going to take this thing, instead of absolute value of t1, I'm going to put this mess over here in equation 2. So see where it says t1? I'm going to put this mess instead. And while I'm at it, I'm going to take the 350 and I'm going to move it over to the other side. So the very first thing I'm going to write down is this term. But again, instead of absolute value of t1, I'm putting this. So we have, so this is coming from equation 2 now. We have absolute value of t2 cosine 50 degrees over cosine 38 degrees times sine 38 degrees. So I just wrote down this term. Now I'm going to just copy this term down, plus absolute value of t2 sine 50 degrees. And it's not equal 0 because we moved the 350 over, so it's going to equal 350. And now the good news is that the absolute value of t2s can be factored out. So we have absolute value of t2 and then a mess over here. Okay, what is this? Cosine 50 degrees over cosine 38 degrees sine 38 degrees plus sine 50 degrees equals 350. And so now to get the absolute value of t2, we just divide by this parentheses here. So it's going to be 350 divided by the parentheses, which I'm not going to write down since I'm a little out of room here. And when you do that on the calculator, you get absolute value of t2 equals, so the answer I'm getting is 275.97. I'm going to go ahead and round that to 276. And then since it's a force, we need to write newtons there. Okay, that's part of the answer. They did ask you for the magnitude of each of the tension forces. There's the magnitude of tension 2. Now, how are we going to get the rest? Well, we can get the magnitude of tension 1 from this equation. Just plug in, we have the magnitude of tension 2 now. So multiply it by that. So we do that over here. We're going to erase this stuff here. So magnitude of tension 1. So again, it's magnitude of tension 2. That's this 276 number times cosine 50 over cosine 38. And on the calculator we get 225 newtons. All right. We're basically done now. Just go ahead and summarize. We've done all the work there is to do. Let me just go ahead and write everything down here. So I have tension 2 is 276 newtons. So there's the magnitude of tension 2. There's the magnitude of tension 1. And then besides the problem asking you to find the magnitudes of these tensions, it said find the tension vectors. So I have to write them down in component form. So, okay, there's a couple ways to do it, but we kind of already did it, so there's no reason to do it again. So here's what we had. I know I've erased it now, but earlier in the problem, we had the tension 1 vector written in component form was, so it's absolute value of tension 1 cosine 38 degrees and absolute value of tension 1 sine 38 degrees. And so now we can just go ahead and plug in the absolute value of tension 1 in here. So absolute value of tension 1 is 225. So we have 225 cosine 38 degrees and then 225 times sine of 38 degrees. And you calculate those in the calculator and you get so you get 177 for the x component. I suppose you should put newtons here and then calculate the y component and I'm getting 138.5 newtons for the y component. So that would be the answer for the tension 1 vector. If they want the answer in component form, otherwise we can use what I talked about in another video and you can write it in magnitude and direction form. So if they don't want it that way, instead you can just write that T1, here's what you know about the vector, so it has magnitude 225 newtons and it points 38 degrees counterclockwise from the positive x-axis. That's an easier way of writing it, but I'm guessing they don't want you to just write it down. So instead, maybe they want the component form. But that's another way to do it. And we knew it was 38 degrees from our picture when we drew it. Okay. And then for T2, same thing. For the T2 vector, when we wrote it in component form, it was, let's see if I can remember, I think it was negative absolute value of T2 cosine 50 degrees, and then absolute value of T2 sine 50 degrees. And same thing, put the absolute value of T2 in there, so this is going to be negative 276 cosine 50, and then 276 sine 50. And if you calculate on the calculator, you get, so this was negative 177, it's 0.4, but I'll just write 177 newtons, comma, and then do the other one. I'm getting 211.4. I don't know what I just said, 211.4. I'm just going to write 211 newtons. If they wanted a component form. Otherwise, you would say that T2 has magnitude 276 newtons and points, why don't we just make it easy and write 50 degrees above the negative x-axis. Okay, so that's the answer to the problem. I'm pretty sure they want the component form though. Not 100% sure, but so here's the answer for T1 and here's the answer for T2. All right, so that's how that goes. The next problem we're going to do is going to be identical to this one, but let's go ahead and do it so we get a little more practice. Okay, the tension at each end of the chain has a magnitude of 25 newtons. What is the weight of the chain? I do understand that chains get confusing. The easiest thing I can tell you, well, maybe it's not easy, but I think it would be easier if you forget that we have this long chain and just imagine a dot. So instead of a chain, we have a dot. And for a lot of physics problems, you just forget the size and shape of the object that we're talking about. You just think of it one dot, and you think of a bunch of forces acting on this dot. So the chain has a weight, so we have a weight force downward. I'll draw it better in a minute. And then it has two tension forces. There's another result about tension forces in a string, and basically the result says that the tension is going to be the same everywhere in the string. And that's kind of why they only gave you one tension force. There's really two, because there's a force pulling on the chain this way. Because it's attached, it's being pulled that way. Because you understand, if there was nothing pulling that way and nothing pulling this way, the chain would just fall down. So something's pulling it that way. It's always in the direction of the chain. I guess this dotted line is the direction of the chain at the end of the chain there. So I guess my arrow's off a little bit. So it should be like this. Okay, so that means we have a tension force here and a tension force here, and those are both 37 degrees. We have two 37-degree angles. I'll draw it better in a minute. But think about it like that. So once again, we have an object that's not moving, but a bunch of forces on it. So I know that from Newton's first law, part of Newton's first law, is that the total force on the entire chain, total force on the dot, is going to be the zero vector. Okay. So let's see here. So what I want to do is I want to write down I'm going to just draw this picture a little bit better now. Actually, just memorize the situation. Let's go to a blank screen here. So I know it's a little bit weird, but think of this as the chain. And we have three forces on it. We have the weight force, the weight of the chain, which is downward. And even though the tensions are the same, when I say that, I mean the magnitude is the same. The directions are not the same. So I do need to call them two different things. Let me call this one T1 again. And the other one here, T2. But I know they have the same magnitude, so that's good. And they both make a 37-degree angle with the horizontal. So once again, the weight force is real easy to write down, so let's write down the weight force first. Oh, one more time, let me put an x and y axis down. So I'm drawing an x-axis so that the object is at the origin. And again, same thing with the y-axis. Okay, so the weight force, once again, is only in the y direction. It's downward. So the x component is 0. The y component is negative. Other than that, what do we know? So they don't tell us what the weight force is. And that's the question. What is the weight? So the length of that vector is going to be magnitude of w. So this is going to be negative magnitude of w. Or magnitude of w is the length of this vector here. But it's going to be positive, but the component's got to be negative because it's pointing downward and the y-axis points upward. That's why we have to put a negative there. Okay, so then let's go ahead and write down the tension forces in their x and y components. So I'll work on the T1 vector first. But they're basically about the same. So here's the T1 vector. And I know this angle right here is 37 degrees. So in that sense, it's easier than the other problem because they already gave us that angle. We didn't have to find it. Now again, to find the components of this vector, I'm going to go from the arrow, from the tip of the vector, downward towards the x-axis. You can go instead to the left to the y-axis if you want. And then the vector that goes from the origin to the spot I just got to, that is one of the components of the vector. And then from the spot I just got to the tip of the original arrow, that's another component. And whichever one's pointing in the direction of the x-axis, that's the x component. The one that's pointing in the direction of the y-axis, that's the y component. So this is the x component. That's the y component. But again, right now, those stand for lengths of sides of the triangle. So after you find the lengths of those sides of the triangle, if one of those components is supposed to be negative, you have to put the negative in yourself. Okay, the problem also tells us that the tension force is 25 newtons. So they tell us the length of this vector is 25 newtons. So that helps us out a lot. So we can just take sine 37, so sine of 37 degrees. Let's see, that's opposite over hypotenuse, that's y over 25. I know it's 25 newtons, but I don't like to clutter up my equation, so I'm just going to put 25 there. And that gives me that y is equal to 25. Oops. So we get y equals 25 sine 37 degrees. And since everything is known this time, the last problem was harder because we didn't know some of those things. Since we know those things, we could just go ahead and calculate it. So sine 37 times 25, and we get about 15. Okay, cosine of 37 degrees, because the triangle is adjacent over hypotenuse, x over 25. That means that x is 25 cosine 37 degrees. And again, you can just put that in the calculator. And I'm getting basically about 20. So the t1 vector, now that I know, okay, so we have the y side of the triangle, the x side of the triangle. Now I have to look and see. But notice that the x component is pointing in the same direction as the x-axis. So it's positive, so you just put a 20 there, no negative. And the y component is pointing in the same direction as the y-axis. So that one's also positive, so you just put 15 there. So there's the t1 vector. Okay, let's go ahead and work on the t2 vector. So as far as the t2 vector goes, you can do the whole thing over if you want. But, you know, because so much of it is similar to this t1 vector, I think there's not much work to do here. But it's up to you. You can show more work if you want. So the t2 vector looks like this. It has the same length as the t1 vector. It's also 25 newtons. This angle is also 37. If you go to find the components, you can go from the tail here to the x-axis if you want. And from the origin to this point here is the x component. And then from this arrow here to the arrow, the blue one, that's the y component. And when you SOHCAHTOA on this triangle, you're going to get the exact same things. You're going to get x is 20 and y is 15. I'll let you go ahead and do it, but it's the same exact thing. But now when you write down the t2 vector, the only thing that's going to change is that you can see the x component is negative because the x component points to the left, but the x-axis points to the right. Whereas the y component points up and the y-axis points up, so the y component is still positive. So when you write this as a vector, it's going to be negative 20, comma 15. All right, so we have all the vectors in the problem, all the force vectors on this chain in component form. And now we're going to use the fact that we know that the chain is not moving. So if something is not moving and it just doesn't move at all, just stays there the whole time, it's at rest and it's remaining at rest, then Newton's first law says that the total of the forces on the object has to be 0. So that tells us that if you add the weight force and the t1 vector, tension vector, and the other tension vector, those are all the forces on the object, you're going to get the 0 vector. Let's go ahead and add them real quick. If you add these three vectors, you have to add the components. So if you add these components, it's pretty easy to see you get 0 because it's 0 plus 20 minus 20, you get 0. If you add the second components, you get negative absolute value of the weight force plus 15 plus another 15. And this has to equal the 0 vector, 0, comma 0. And as I said before, when you have two vectors equal, then the components have to be equal. In other words, they have to have the same x component, which they do. They both have a 0 there. And they must have the same y component. That means this whole mess here, y component has to equal the y component here. So we get negative absolute value of the weight force plus, okay, it's plus 30 equals 0. And so you get the absolute value of the weight force is 30. The units, newtons. And that's the answer to the problem. They asked what's the weight of the chain. Weight of the chain is 30 newtons. Yeah, that's how that one goes. Okay, guys, that's it for that video. Study hard.